Learn like a pro.
All right, let's dive right into the heart of the matter, literally. We're going deep, deep inside the atom today to look at its fundamental architecture. We're going to tackle a really big question. Why are some atoms just unstable? And what actually happens when they decide to change? This is the wild story of nuclear decay. So picture this. At the very core of every single unstable atom, there's this epic tug of war going on. On one side of the scale, you've got these incredible nuclear forces. Think of it as the universe's strongest superglue, holding all the protons and neutrons together. But on the other side, you've got these repulsive forces, constantly trying to shove everything apart. And when that scale tips, just like you see here, well, instability takes over, and the nucleus is forced to do something, anything, to get back to a stable state. Okay, so before we can get into how a nucleus actually fixes itself, we've got to properly diagnose the problem, right? We need to dig into this unstable foundation and figure out exactly why that scale tips to begin with. And that fix has a name: radioactivity. It's basically the nucleus's own built-in natural mechanism for letting off steam, for releasing all that excess energy. By literally throwing out a particle or a wave of energy, that unstable nucleus can finally chill out and settle down, transforming into a much more stable version of itself. Now, this is where things get really fascinating. This whole process is governed by two key principles. First up, it's totally spontaneous. What does that mean? It means nothing from the outside world can trigger it. You can't heat it up or squeeze it to make it happen. It just happens. And second, it's completely random. We have absolutely no way of knowing the exact moment a particular nucleus will decide to decay, or even which direction the radiation is going to shoot off in. It's pure chance. So that leads us to the how. How does it actually happen? Well, to relieve all that internal pressure, the nucleus basically has three main escape hatches it can use, three different paths to get back to stability. And here they are, our three main players. First, the nucleus can spit out an alpha particle. This is the heavyweight of the group, made of 2 protons and 2 neutrons all bundled together. The second option is to fire off a beta particle, which is just a really, really fast-moving electron. And the third choice, it can release a gamma ray. Now, this one isn't a particle at all. It's just a pure, high-frequency blast of energy. Okay, but hold on a minute. Did you catch what I just said? A beta particle is an electron that comes from inside the nucleus. How on earth is that possible? We all know the nucleus only has protons and neutrons, so where in the world does this electron just pop out of? And here's the answer to the puzzle. It's what we could call the beta anomaly, and it's pretty wild. It's not like there was an electron hiding in there the whole time. Nope. What actually happens is that one of the neutrons inside the nucleus just transforms. It changes, splitting into a brand new proton, which hangs around, and a brand new electron. And that electron gets kicked out with incredible force. That ejected electron, that's your beta particle. Mystery solved. All right, so we know what these things are. Now let's talk about their unique signatures. You see, alpha, beta, and gamma radiation, they each interact with the world in a totally different way. They each have their own distinct material fingerprint. And this little matrix here just lays it all out perfectly. Let's break it down. Look at the alpha particle. It's heavy. It's got a positive charge, so it has this incredible ability to ionize other atoms. That just means it's really good at smashing into things and knocking their electrons off, causing all sorts of chemical changes. Then you've got the beta particle, much lighter, kind of in the middle. And finally, the gamma ray. No mass, no charge. It's not very good at ionizing at all. But here's the kicker. Watch what happens when we look at penetrating power. The whole story flips on its head. This visual just makes it so clear. That alpha particle, think of it like a bull in a china shop. It's big and powerful, but it's also clumsy, so it gets stopped by something as flimsy as a piece of paper. Your skin stops it. The beta particle is a bit zippier. It'll go right through paper, no problem, but a thin sheet of aluminum will stop it in its tracks. And then there's the gamma ray. It just sails right through both of them like they're not even there. You need thick, dense lead or a whole lot of concrete to even slow it down. So what's the big takeaway here? It's this one simple rule. There's an inverse relationship going on. The more mass and ionizing power something has, the less it can penetrate through stuff. And it works the other way around too. The big old alpha particle causes a ton of damage, but runs out of steam almost instantly. Meanwhile, the lightweight gamma ray can travel a really long way precisely because it barely interacts with anything it passes through. Okay, we've covered the why and the how. Now it's time to learn the language. Physicists have this really neat, precise shorthand for mapping out all these changes, and believe it or not, it's actually super easy to read once you know the secret code. So the key to the whole thing is this symbol right here. X is just the letter for the element, like U for uranium. The number on the bottom, Z, that's the proton number. This is the important one. It's what defines the element's identity. And the number up top, A, that's the nucleon number. That's just the total count of everything in the nucleus, all the protons and neutrons added together. And with that symbol, we get these two simple rules for the transformations. For alpha decay, remember, the atom is spitting out 2 protons and 2 neutrons. So the math is easy. The top number, A, goes down by 4, and the bottom number, Z, goes down by 2. Then there's beta decay. Remember our little trick? A neutron turns into a proton. So the total count on top, A, doesn't change at all. But since we gained a proton, the bottom number, Z, goes up by 1. And just like that, you've got a whole new element. Let's put this into practice with a real-world example. A classic one, uranium-238. Okay, so it starts with 92 protons. It's going to go through alpha decay. So what's our rule? We just apply it. We subtract 4 from that top number, 238, and we subtract 2 from the bottom number, 92. A little quick math, and we get a new top number of 234 and a new bottom number of 90. So what element has 90 protons? You just grab a periodic table, look it up, and bingo, it's thorium. See? Simple as that. And this, right here, is where it all clicks into place. This is the cascading decay architecture. See, an unstable element almost never gets stable in just one go. It's more like it tumbles down a flight of stairs, a whole chain of transformations. You can see it in this blueprint. It might spit out an alpha particle and become a totally new element. But wait, that new element is also unstable. So then it might shoot out a beta particle, changing its identity again, all the while releasing its extra energy as gamma rays. And every single step in this chain follows the exact rules we just figured out, creating a clear pathway to a final, stable atom. So think about it. We've gone from a tiny war inside a nucleus all the way to learning the secret language that describes it. You now have the basic tools, the fundamental keys to read the blueprint of nuclear decay. So the real question isn't what we've learned, but what you'll do with it. What other atomic stories, what other elemental transformations out there are you ready to decode?